Hello, today's lesson is on the topic of infinite series, and our objectives are, number one, you will understand the definition of an infinite series. Number two, you will understand what it means for a series to converge or diverge. And the third one is you will find the sum of a converging infinite geometric series. Well, let's first introduce what is a series, because in the last lesson, the topic was what is a sequence. And the best way to define a series is just to think of it as adding together the numbers of a sequence. So in the previous lesson, if a sequence was just a list of numbers, maybe denoted like this, a sub 1, a sub 2, a sub 3, the corresponding series is to take those numbers and simply add them together consecutively. And so you notice we often will compact that into our summation notation or sigma notation, such as this one here, where k is counting the numbers up the list. A sub k is the general term. In this case, though, that represents just the numbers of our sequence. And the sigma is telling us to add them together. And the upper number, or infinity, tells us to add indefinitely. And when that infinity is there, this is called an infinite series, which means we're supposed to add and add and add forever. If we stop the series at any given time, we're converting what's called a partial sum. In other words, the sum of, say, the first 5 numbers, or the sum of the first 10 numbers, etc. And if I do that, if I take successive partial sums, I'm getting a sequence of partial sums, which means maybe I look at the list of partial sums, adding the first number, then adding the first 2 numbers, then adding the first 3 numbers. And we're going to examine that principle next as a good way to determine that if I add and add and add more numbers, does that sum get larger and larger, or doesn't it? Turns out that sometimes it does, sometimes it doesn't. So let's investigate this a little bit further here. I have an expression that will generate an infinite series. And what we're going to do is we're going to add together successive longer lists of numbers and see what happens to the sum. Now I'm going to try the first few, but then I'm going to encourage you to pause the video and try and fill out the remaining few rows here. So let's just first write out the first few numbers of this series. The general term is 1 over k plus 1 times k, where k is starting at 1. So the first term is going to be 1 divided by 1 plus 1 times 1, which is 1 over 1 times 2. And then if I keep going the next few times, it'll be 1 over 2 times 2 plus 1, 1 over 3 times 3 plus 1, and so on, supposedly forever. Okay, so what I'm going to make a list of now is a sequence made by adding successively longer lists of these numbers. So in the first row, I'm adding up just the first number. And that would be the sum of just the first number, which will be 1/2. Partial sum number 2, which we're going to call S2, is going to be the sum of adding the first 2 numbers, which is 1/2 plus 1/6. And if you just try this, maybe it's mental math for you, maybe it's not, but 1/2 is like 3/6, and 3/6 plus 1/6 is 4/6, and then that reduces down to 2/3. The third would be adding the first 3 numbers together, which is 1/2, 1/6, and then 1/12. Now, shortcut would be to take the previous answer 2/3 and just add on the 1/12. Okay, so if you think about that, if 2/3 is equivalent to 8/12, then adding on one more is going to make 9/12. But that reduces down, dividing everything by 3, to 3/4. Okay, I would encourage you to pause the video right now and try and add up and try and complete the next couple of rows, like adding the first 4 numbers in this list, then adding the first 5 numbers in this list, and then I'll be back in a second to help to see if you can check that. All right, go ahead and check your results with what I've got. I added up the first 4 terms now, which went all the way from 1/2, 1/6, 1/12, and 1/20. The sum total was 16/20, and it reduced down to 4/5. Then I added the next 5 numbers, which is the first 4 plus the extra term 1/130. And after reducing it, it was 5/6. So now let's just focus on the 5 results. So in other words, the sums S sub n is this sequence right here. 1/2, 2/3, 3/4, 4/5, 5/6, and so on. So the question is now, do we think, considering that as a sequence, A, do we think we can find a rule or formula for this sequence? And if we can, we ought to be able to see if there's a limit. Well, just making an observation here, it looks like in every term, the numerator is always 1 less than the denominator, while the numerator is always the number n. And so it looks like the rule for that sequence is n over n plus 1, which means I can now take and look at the limit, which would represent what is going to happen if I add more and more and more of these numbers together. So instead of adding just the first 5, what if I added the first 10? What if I added the first 100? What if I added the first 1,000? According to my sequence of partial sums that led me to this equation, this expression, for example, I now know that if I added the first 100 numbers to this list, my sum would be 100 divided by 101. And so I can take that a little further and ask what would be the ultimate limit if I added up forever. And we know from studying limits that this has a limit of 1. Notice the n is the degree 1 in both the numerator and denominator. So the limit ends up being this coefficient 1 over this coefficient 1. So what we're saying then is this series, this infinitely long sum of numbers, can be added indefinitely, and I will get my successive answers are going to get closer and closer to 1. It doesn't mean I'm ever going to be able to get a sum of exactly 1, because I'm actually not going to be able to, but I can make the answers as close to 1 as I wish by just adding more numbers. Let's try it again. So this time I'm going to compute the first 6, or maybe a little bit less than that, of the partial sums of this series right here. And we're going to decide if we think this one's converging or not. So let's write out the first few again. And the terms this time are 1 over 2 to the k. So the first term is 1/2, and then 1/4, and then 1/8, sorry, 1/16, and so on like that. So the sum of the first number only is 1/2. The sum of the first 2 numbers is 1/2 plus 1/4, which is going to make the answer 3/4. The sum of the first 3 numbers is going to be the previous sum 3/4 plus 1/8. Which is going to make the answer 7/8. Let's try, and I'm going to, again, I encourage you to pause the video for a minute and try and work the next couple of rows out yourself. And I'll go ahead and complete them in a minute. Welcome back. I just added up the next couple of rows as well. You can check maybe what you got. And my list of partial sums now goes like this. Adding just one number in the list made 1/2. Adding the first two numbers in the list gave me an answer 3/4. Adding the first three numbers in this list made the answer 7/8. And then I got 15/16, and my fifth one was 31/32. I'm noticing again that there's a little pattern here. Looks like the numerator is always one less than the denominator one more time. This time, though, the denominators progress by powers of 2. So this is 2, 4, 8, which means that's 2 to the power n. And then the numerator of the sum is always 1 less than that. So I would write the numerator 2 to the n minus 1. So in other words, if I wanted to find the sum of the first 1,000 numbers, I can get it by taking 2 to the power of 1,000 minus 1 all over 2 to the power of 1,000. And at that point, you notice that the ultimate, that value is really, really close to 1 again, because the bigger n gets, the less significant the minus 1 is. And so I could argue that the limit, as n approaches infinity, 2 to the n minus 1 over 2 to the n is 1. Once again, I have a sum for which I can add infinitely many numbers together, and I'm never going to get a sum bigger than 1. In fact, the sums are going to get infinitely close to 1. And so in both of those first two examples, we would say the series, which is the sum of these numbers, converges because the sequence of partial sums converges.